OpenFOAM is a software package, just for who don't know. It is like a very, I think it's in open source world, I think it is picked up very well and taken up by various automotive company for CFD simulation. So you can see this is a motorbike, and you can see the entire mesh, and we do the airflow analysis across the body of the motorbike. So it is a, if you see the code of OpenFOAM, it is written in pure MPI, and it's the way it is written is very good, and it's very highly scalable application. Also, it is a C++ code and heavily STL code, the standard template library, and very difficult to understand this code and very difficult to optimize. Tell me, it's a nightmare to optimize this application. And so various benchmarks is being done. We have done optimization on KNC as well. We have changed various things in last year, but KNL is a different experience altogether. So this is what I have talked about at ISC, the 3 parts of the optimization. So I'm going to touch over so that everybody gets an overview, and then we'll talk about the various aspects. So OpenFOAM has lots of hotspots. So one of the hotspots is a Gauss Seidel smoother, which is kind of sparse matrix problem, where you have this each rank. So I'll just talk about, I'll just go there. So you can see this is a hotspot which is taking around 17 to 18% in OpenFOAM. So what it does is, this is the code run by each rank, and each rank is going over each cell, and these are the 2 devil for loops inside this, inside the main for loop, which is creating lots of problem, because lots of unaligned access you can see here, scatter, gather, and so this code is not vectorized by default. There are lots of problem, and this is a completely memory bandwidth application. In OpenFOAM, we saturate the bandwidth of the system, whatever. If you talk about Broadwell, we are hitting around 65 or around 62 per socket kind of, and here in KNL we are reaching up to 361 on. So it is very highly bandwidth bound application. So in this, what we have done, if you see this is the by default code of the compiler, and what happened is, if you see this f length is unknown. So each time this cell loop, if you see the previous, you go over this each cell, you have a number of faces, and this is very dynamic. You don't know that this is a stat, like what is the number of faces. It can be goes from 3 to 24 or whatever. So you don't know, compiler doesn't know how to vectorize this during the compile time. So you can see this here, the first loop is not vectorized, and also because we are using the FP precise flag, and we cannot avoid that, because that will impact the performance. The second loop is doing, but it is doing the conflict detection. So if you see this first vec report, it is showing that it is not vectorized due to FP model, and the second loop is doing it, but it is having some conflict detection. It has a Moro head. So we played around with this and lot, which I spoke at ISC. This is a second loop, peel and remainder loop, and talks about. But you can see this is what we have to do at the end. So we can see the intrinsics. We have converted this entire code into intrinsics, and we got 2x improvement in this loop, only in this Gauss Seidel. And then the same learning we have taken it to other hotspots like AML, residual, and summary. There is various functions which comes in a VTune hotspot. So we applied those intrinsics, and we got a huge improvement because of that. So minimum is 8% to 10%, I'm saying. So depend on the kind of workload we are taking. The second one is this memory consumptions. As I said, OpenFOAM is completely bandwidth bound. So we wanted to see that why the bandwidth utilization is so high. So we use various tools, but I think we wrote our own kind of tool or profiler, where we found out that there are lots of peaks are happening during the profile, and we identified those peaks. And what we have done is, these peaks are because lots of allocations are happening during the iterations. So this peaks, we know that there are lots of temporary variables are getting generated, and this temporary variable I am talking in terms of 100 MB, 200 MB, 300 MB of size. So can we see something that we can improve that? So what we have done, So this is a very small example. Just wanted to show that here there is a vector and tensor. Tensor is a bigger vector, you can say, and it is each tensor for a smaller workload it goes up to 100 MB, and they multiply and they create a temporary variable of they multiply and they create a vector only. But once you call this interpolate function, it creates a tensor and returns a tensor, which is a costly thing. So what we have done, we have created our own function, and this changes we have given back to the OpenFOAM now. Now if you download the OpenFOAM latest version, you see these changes, what we have done. So this optimization, so we created a new function, if you wanted to see what it does, the old function is tensor into tensor, and it is creating a tensor multiplication and returning a tensor. Here we are changed that part and completely just returning a vector. So you can see that you save this tensor variable which you were creating before, now you're just creating a vector and you save lots of memory. So you can say around footprint went down up to 1/5 for this particular loop, and we got around 4% improvement because of this. And the third one is which during the tutorial I was talking about, that HBM lib, the high bandwidth memory lib. So what it does is, so basically in lots of discussions going on since yesterday that we have to divide the workload between MCD RAM and DDR. How effectively you can do it? So what it does is, for OpenFOAM, what we do is we decided, okay, so this is a simply wrapper, which what it does is uses a TBB allocator, and what it does is it will during the runtime you do the exports, and during the exports you can just set some this data. You can say that I want 16K data goes to MCD and the less goes to DDR. So what actually the Intel memkind and this auto HBMW does, but this is almost 3 times better performance than Intel memkind right now, what we have benchmarked. So Paul from Intel has developed this, and he actually contributed back to the OpenFOAM. So in a week you can see this. So it does few things. One thing is the size you decide. Second thing, what it does is, every time when you run the application on the KNL, for each rank it divides, so it divides 16 GB by number of ranks, and let's say you have 68 ranks. So this amount of memory it allocates dedicated to that rank, and say that okay, you have fixed rank and you keep it back and never release back to the OS, because you do lots of allocation, deallocation, allocation, deallocation, so it do some penalty. So this you can do using 2 malloc exports are there, which I have shared before. So because of this HBM lib, we have seen some improvements in the, and this is only applicable to flat mode. So we have seen some improvements. So we're going to discuss about this in detail in the slides, which I'm going to cover. So this is the agenda today. So based on those optimization we applied, and this is the agenda I'm just going to talk about. That intrinsic code, people are saying that okay, yes, you're getting the benefit and there's no alternative to it. So I spoke to the Intel compiler team, and thanks to George, who actually come up with the way we can actually remove the intrinsics and come up with a templated code. I'm going to explain that. The second part is we have compared the GCC versus ICC, and there is a very good readings. I think you can also try in your application and tell that which is better. So whatever is better. So we compare the memory modes, like on KNL for OpenFOAM, what size of workload you should run on the one node, and on the cluster, which mode is also better, like this flat mode, cache mode, and we compare with the Broadwell. And then the benchmarking results for single node, and I'll just show the number, latest number, and the cluster. So this is the code that the intrinsic code I've told you. So this is the replacement of that. So what here we have done is, if you see this loop, what I was talking about before. So in this loop, this f start minus f end, the f length was unknown before. That's the reason compiler was not able to vectorize it properly. So what we have done, we have written this code in such a way that in a switch case statement, and you can see this each one is a template function, and we decide that okay, for each length we just call and create a templated code. So compiler does a very good job while doing the assembly code generation for this particular code, because here you know that at a compile time what is the f length. So if your this cell loop runs. So each cell, if the face is 3, it will go to the 3 and it generate the code for 3. So the vector length and everything, it just over whatever overhead comes by default by the compiler that we have seen before in the intrinsics. So this works well, and I think if this has a very good acceptability also in when we have been talking to the OpenFOAM owner, and in other applications, if you see the intrinsics you are doing, you can try something like this, and because this is very generic code. Another point is in intrinsics code, we need to maintain KNC version differently, KNL version differently, different intrinsics APIs are there. It's a bit headache to maintain and different versions. So this is a benchmarking configuration that I'm going to talk in the further slides. So these are the your flags that we have used for GNU compiler. This is 6.1, and then for ICC is 17.0 beta, and this is the flags that we have used, and this is the configuration, the Broadwell and the KNL. So this slide is bit complex, but I'll just take you through how easy we can discuss. So let's see that first compare the intrinsics versus template, because that is a major challenge in order to accept this. We are comparing intrinsics versus template. So start with the ICC. If you see this, this is a ICC intrinsics and this is a ICC template code. Then you can see that ICC with the 68 ranks on single node, IC for 11 million code, this is better. So we said okay, but when we ran this on with the GCC is a little bit better. So don't go by this only 5 seconds improvement, because when you run the iteration for 1000 times, this number will be a huge difference. So you can see this, the 68 ranks GCC template code is better. GCC does not have an intrinsics API or complete support right now, so we just use the template code. Then we compared the 136 ranks. Almost all of them are near about simple, only the ICC is worse, but ICC intrinsics and GCC template is almost same, because 136 ranks you are hitting some system limit, which is, I know this is a memory resources that you are hitting, but we need to prove it. So we are working on it. So one very, I'm not sure if you heard about the power heat, that what we have seen that in the ICC versus ICC intrinsics versus GCC template, the VPU utilization of ICC was very high, and for this GCC was less. So maybe we are trying to understand, is it that because of power hit, because the VPU utilization is high, the CPU scale down, the scaling governor of CPU scale down, and that's why the ICC is not giving you the better performance. But we need to ensure and confirm that. The team is working on it. So you can see this. If you see this, GCC is clearly better on template than ICC. You can see around all this thing, GCC of template code for 68 and 3136 rank is better. So you may want to try this, but this is what we have seen, and we are working with the Intel team to try to optimize the Intel code, Intel compiler. And this number is with the flat mode with HBMlib, what I was talking about. So yeah, so this is the numbers that we have taken in order to understand which mode is better. So here the flat mode, if I'm talking about flat mode, means I'm talking about with HBMlib library. So the HBMlib library is giving me up to 5% improvement as compared to normal flat mode. So you can just start with that. So let's take this HBMlib with flat. So we have benchmarked 4 million, 8 million, 11 million, and 20 million. So generally 4 million up to 8 to 9 million workload fits in your 16 GB MCD RAM. So you can see this, the workload which is fitting well or little bit spilling over, you can see that the performance of flat mode is better than cache. The moment you have a higher number of million, which is 11 million, which is way more than 16 GB of MCD, you can see there is a cache mode overtakes, and after that you can see this with 20 million case, cache mode is much better. So this gives an idea that what modes you want to run. So it depends also that how much amount of working set size you are assigning to one node. If it is very well fitting under 16 GB or almost on the border around 20 GB. So you can say that you can use the flat mode using HBM lib. But if it is way beyond that 16 GB, then I think the cache mode is better on the cluster. So this is and one of the point I just wanted to bring up here is if you're using the smaller sets like this, like up to 8 million or 9 million on one node, and you have a cluster of nodes. So for automotive customer, flat mode is better, and this 5% is only for 100 iteration, and they are running thousands of iterations. So you can see the difference. It will be the difference is very high, and you get a good improvement. So this we need to consider. So this is give a very, so we ran various runs and different workloads, and the cluster runs also we'll see, but this gives an idea that if you are having a very high working set size, cache is always better. Yeah. Yeah. You are saying if I go for the cluster and if I select the cache mode. So even so cache mode is the cache mode benefit only comes into the picture when your working set size is, let's say, 40 GB or 30 GB. So you, or maybe, yeah, yes. So this is the case when you're taking this. So this is a 4 million case, and I'm taking only 100 iteration difference. So this simulation I ran for 100 iterations. If I ran, actually this iterations ran for 1000 iterations, 10,000 iterations for our customers. So then you can see the difference. Then this difference will be high. Not, yeah. So that is a point here. But if so, let's say you have a 100 million car case, and you want to distribute over 10 nodes. So I think that case, what we understand is the flat mode is better, because up to 10, the flat is better. But if you are saying that I have a 100 million case and I have only 5 KNL nodes, so in that case, the cache is better. Yeah. So in this case, in 4 million case, we are taking around 11 GB. Yeah, 11 GB. And for 20 million, you can extrapolate, but I have not calculated, but it is way beyond 16 GB. You just crossed it. So this 8 GB is also around 20 GB. 8 million is also around 20 GB. So you just spill over by 4 GB. So yeah. Okay. Yeah. So this is a single node number that I have. Like this is a Broadwell. So Broadwell, we did not see any improvement because the intrinsic template is not required here. Only the memory changes are affecting here. But here, this is a 136 rank difference, and I am seeing here the 12% difference. But this green bar, the baseline one, I have used HBM lib. If I don't use HBM lib here, this is 5% worse. So you can see around 17% improvement that we got because of the improvements total between baseline and optimized using flat mode. So this is a cluster run for very small case, and the bigger case we are just running out 100 and 200 million. We are validating more results, but in this case you will get some idea that what is happening. So you can see this. This is a 68 rank, the green one in the flat mode. This is the 136 rank with the flat mode, and this is a Broadwell. So 11 million on, you can say 1 node, 2 node, 4 node, and 8 node. So till 4 node, I think the marginally the 68 ranks is better. Your KNL with 68 ranks, till 4 nodes. So, you can say if you say 4 node and 11 million. So, you can say roughly about each node have 2 point some million mesh size, which is, so it is way under the 16 GB of consumption. So, 4 million this 11 by 4. So, you can say that it is with the KNL also you are increasing the more ranks also as compared to Broadwell. So, you have more ranks and you have less data to give it to the KNL core for the compute. So, in the previous slide I mentioned that at least on the KNL we should give for memory bound applications around 9 million for OpenFOAM case, let us say. So, which consumes at least 20 GB or 24 GB. So, then only you can see the difference. In this case 11 by 4, which is around 2 point something, you are giving to one KNL and you are increasing the rank with 1, 2, 4 nodes. So, you can see you have the trade off here, that as soon as you hit the 8 node, the Broadwell took over in the performance. So, you need to decide that you need to give proper data to each KNL node for the scaling, and also the number of ranks also plays important role. So, we ran I did not show the number here, but 100 million with we go up to 32 nodes, and as after 20 nodes I can see the Broadwell took over, because the number of ranks is also increased and number of working sets you are giving to each KNL is very less. And the main point is, who is going to buy KNL only for running 2 million or smaller workload? They wanted to run bigger case, right, at least 8 million or 9 million. So, this is the insights that what we have discussed till now, that intrinsics always give a better performance, but when you are not able to vectorize the code, but template is an option that is, if you just tell the compiler forcefully that okay, at the runtime what is the length and whatever optimization we have done. So, one of the question asked in the reviews of this presentation, that somebody said this can be used by other application as well, where we can remove that intrinsics part. Can we tell compiler in such a way smartly in a user friendly language that no need to it will do the job what you want. So, so this is a point, 2 points mainly I wanted to make here is for smaller cells per node, where memory required is up to 16 GB, flat mode with HBM performs better, which I told. As the number of cell increases, cache mode performs better. The second point is, even though the Intel Xeon Phi does not scale like, so Intel Xeon Broadwell scaling is very good if you talk about 32 nodes or more than that. So, it depends on how you are using the MCD RAM, what type of data how much size of data you are allocating, and how you are using the MCD RAM benefit. If you're not using the MCD RAM completely, like you're just giving a smaller size or giving overpopulated that will also give a penalty here, and you end up having the problem of using MCD RAM with the improper allocation of the data. Plus, definitely KNL cluster has lots of ranks as well as compared to Broadwell, so you have that penalty as well. So, this is, I'm just going to stop with me. I think I'm done with my talk, so open for the QA. Yeah. So, it's a bin 1, the latest, I think the configuration, this one. Yeah, Intel system. Yeah.
You measure performance in terms of flops per second for single KNL node?
No, I have not done. So, I think I need to do that. I have not done that. Yes.
Sure.
The focus was to get rid of intrinsics and get the better, at least what performance we are getting and running the cluster, but we want to do that. So, and one more thing, it is a bandwidth bound, so it is the consumption is very low. I think the flops, what you are saying, usage is very low. So, you need to use the roofline model what Jack is, I think, going to discuss tomorrow. So, I think I will do that.
DRAM bandwidth.
Sorry?
Don't know if you saturate MCD RAM bandwidth.
So I am saturating the.
You have like 450.
Yeah, so I can see the utilization, that how much is free, and I can just, when I say the more than 16K data structure go to MCD or less, rest go to DDR. So definitely for bigger workload, I know that, and I check the free usage, how much MCD is utilized. So I can very well see that.
You were talking about some pretty small differences, like 10% or so in the runtime, and I was just wondering how much variation do you see if you just run the same run many times?
Generally runs for at least 10 times, and whenever it's constant, so we can see, you can see 1 second or only 1 second difference in the runs, but it's almost we are getting the stable numbers.
Okay, thanks.
This numbers what we are seeing the differences only for small iterations, because we are just doing the optimizations right now, but finally when we are going to run the cluster with the bigger iterations, I think we are going to see the more results.
So you said you're bandwidth bound, but you said that the application was bandwidth bound when you started, and then vectorization helped. So how have you determined that you're bandwidth bound, and what bandwidth are you actually seeing from MCD RAM?
So the first thing I am bandwidth bound is because we generally, when we profile using the VTune, you can easily see that, which I showed in the ISC, that every time, most of the time I am hitting the peak, and it is 360 GB per second. Most of the time when it solves the pressure, momentum and turbulence K omega. So when it calculates, you can see the peaks in the timeline of the memory bandwidth. So if you see my memory profiling, you can see the peaks as well. When I remove those peaks, I see the improvement.
Sustained bandwidth bound. That's what I'm saying. There's some kernels that are bandwidth bound.
Yeah. So but it is an iterative process. So these iterations are so you have multiple iterations, before converging. So let's say we are running for 100. So every time those same code equations are running, and you see the hits, it is hitting the bandwidth. Yes. So you're talking about this particular, just a second, that's the one, right? So we actually converted into the if you see this code, I converted into the multiplier, and I moved some part of code before the loop, which I'm not showing here. So your division is very heavy operation, so you convert it into this. So this is a new data structure we created before the loop. Yeah, and this code is all the codes what we are doing. It's I think we have given to the OpenFOAM. So in OpenFOAM now you can see a new branch for KNL. You can see all HBM libs and all the codes that we are doing. We are checked in. So
okay, we will move on to our next presenter. If you have more questions, I'm sure Nishant will be available at dinner.